Okay, now we're going to continue our discussion of wave-particle duality. And again, we're talking about the atoms and the strange things that happen there, and light. Is light a wave? Is it a particle? Is it both? So our objectives are to calculate the wavelength of a moving particle and discuss momentum for photons, which is kind of neat because momentum means mass times velocity. Now, we know that electromagnetic radiation has a particle nature. And again, the easiest way to understand that is photons begin life and die as particles, and then they move as waves. And for me, that's the easiest way to think about it. When light is created, it behaves more like a particle. When it's absorbed, it behaves more like a particle. But while it's moving, it really behaves more like a wave, is probably the simplest way. So now, if electromagnetic radiation has a particle nature, do particles have a wave nature? Now, Einstein hypothesized that photons can have a momentum even if they have no mass. And it was kind of neat the way he comes up with this. But again, he thought about it. It couldn't be proved while he was alive. But it was pretty neat. Now, we know that momentum in general is mass times velocity. But electromagnetic waves move at c. So momentum is equal to m times c. Here it is. E equals mc squared, famous equation. Well, if I expand that, I get E is equal to mc times c. Hey, P is equal to mc, so therefore E is equal to pc. So the energy of a photon is equal to the momentum of the photon times c. Now that only works for photons. I can't use that E equals pc equation for anything except light photons. I can't do it as soon as you have a mass, I can no longer use that. Remember, masses don't move at the speed of light, so therefore I can't use that. I have to go back to a traditional kinetic energy equals 1/2 mv squared equation. I mean, that's important. Key thing is it only works for photons. You're going to see that equation and want to grab it. You can only use it if you're talking about a photon of light. Now, the Compton effect kind of proved it. And this was done, I don't remember the exact date, 1950-ish. What Compton did was he shot an X-ray so it collided with an electron. And what he got was a photoelectron being emitted, similar to the photoelectric effect. He had a photon being emitted from an electron. Now, the original X-ray came out and was scattered, but it was emitted with a lower frequency. Lower frequency means lower energy. So therefore the photon lost energy and momentum. It was still there. But now we had an electron which gained energy. So the conclusion from this was that photons have momentum, and also that photons obey the law of conservation of energy and momentum. So the rules don't change. Now, the de Broglie wavelength. De Broglie said that electromagnetic waves behave as moving particles. So what he was kind of doing was kind of the reverse of what Einstein was doing. What he was talking about was waves and particles and putting them together. He said moving particles exhibit wave properties. So he said that they're both. It was confirmed by the Davidson-Germer experiment, in which he put electrons, he shot a stream of electrons through double slits, and they were actually bent around that. Well, the bending of waves through a slit is a wave property. So therefore he said, okay, electrons are particles, therefore they behave like waves. We're still making that debate now. Smaller particles have more wave properties. Larger particles have more particle properties. So lambda is equal to h over p is the de Broglie wavelength. Now let me show you how they came up with that. We know that E is equal to hc over lambda. We've used that a bunch. Well, don't forget now that lambda is equal to hc over E. Now we go to what Einstein said. E is equal to p times c. The c's cancel out. I have E is equal to h divided by p. And we've extended this to belong to anything. So therefore, as long as I know the momentum, I can calculate the theoretical wavelength of anything. So now, let's look at a couple sample questions. Moving electrons are found to exhibit properties of particles only, waves only, both, or neither. Well, neither we can throw out right off the bat. They sometimes behave like particles, they sometimes behave like waves, so therefore it's both. They diffract, which is a wave property. They bounce off and cause things to move, which is a particle property. So both is a winner. Now, which best shows that matter has a wave nature? Well, momentum is primarily a particle nature, so we can get rid of those, although you can make a debate, like Einstein did, that momentum is also part of it. Diffraction is clearly a wave particle, and we notice diffraction with electrons, so therefore it's electron diffraction. Wave-particle duality is most useful in working with, is it big things or little things? Little things is a winner, so therefore it's an electron. Big things behave more like particles. Our traditional understanding of momentum and kinetic energy and all that stuff works better with big particles. So let's calculate the theoretical wavelength of a tennis ball, 57 grams, moving at 30 meters per second. So I'm going to say lambda is equal to h over p. It's called the de Broglie wavelength. H is 6.6 times 10 to the negative 34th joules times seconds, divided by, well, momentum is mass times velocity. 0.057 kilograms times the speed of 30 meters per second reduces down to 3.86 times 10 to the negative 34th meter. So that's the wavelength of it. Now, my thinking of it is this way. Remember that electrons are moving around the atom, and it's a cloud, and you don't know exactly where the electron is. So the outside of an atom is always changing shapes. Well, if it's always changing shapes, to me, it looks a lot like a wave. You're going to have highs and low spots. There's not a very big difference in them. So to me, that's where that number comes from, and the fact that the outside of your skin is actually slightly moving and slightly vibrating. Bizarre, but true, we think. Now, let's look at pair production, because pair production is something that's pretty neat. It's the creation of an electron-positron pair by a gamma-ray photon. It has to be a high-energy photon. In this process, the photon disappears, and its energy is converted into an electron and a positron pair, and the kinetic energy they carry. So a portion of the energy of the photon is turned into the rest mass. In other words, I create an electron that wasn't there before. Now, we've so far only observed this with high energy gamma rays. But guys, what that really means is, if I get the energy of a photon and out of that I get rest mass plus the kinetic energy of the particles, I'm creating mass from energy. Now, we go the other way around. We create energy from mass a fair amount. That happens anytime in fission and fusion. But the fact that I'm creating it out of just a photon, I'm creating mass. It's one of the few places we've observed mass being created. We observe energy being created every day you look at the sun. Don't look at the sun unless you're wearing sunglasses. Hope this helped.